Hello, geometry. I'm going to go over chapter 5, section 2, perpendicular bisectors. A perpendicular bisector is a segment, ray, or line, or even a plane that is perpendicular, and that, by the way, means that it has a 90-degree angle with a segment at its midpoint. So perpendicular stands for 90 degrees. Bisector means midpoint, and a segment. So it has to be a line segment. And if a line, most likely it'll be a line. Sometimes it'll be a ray or another segment. But it also could be a plane. But we're going to usually see a segment or a line, sometimes a ray, going through a line segment right at the midpoint meaning exactly in the halfway. So whatever the distance from P to B is, it'll be the same to go from P to A. So a point is equidistant. So here's another word. So there's a lot of terminology here. A point is equidistant from two figures if that point has the same distance from that figure. So of course P will be equidistant from AB. But what's significant about equidistance? Why do we have that term? Any point, actually, any point on this perpendicular bisector will be equidistant from the endpoints of the segment. So the distance it is from C, this point here, to A will be the same as the distance from C to B, and that's what they mean by equidistant. Alright, so we have a theorem here, perpendicular bisector theorem, and we're going to use the definition of equidistance in it. In a plane, if a point is on a perpendicular bisector of a segment, then it is equidistant from the endpoints, just like I said. That's exactly what I was just saying. So point C, will be the same distance from A as it is from B. There we go, equidistance. That means that the length, those distances being those distances being the same, mean that those two segments are congruent, or that the lengths, CA is equal to CB. That's the distance from CA to CB, which I already said. We have the fact that a point on a perpendicular bisector, if a point is on a perpendicular bisector, then it is equidistant from the endpoint. Well, the converse of that would be if a point is equidistant from the endpoints of a segment, then it must be on a perpendicular bisector. So maybe it's not shown, but if you know that D is the same distance from A as it is from B, then there would be a perpendicular bisector that would extend through D, a line that would extend through D. So that would have to be the case. So it goes both ways. Both if you have a perpendicular bisector, a point on that line will be equidistant from the endpoints. But if you have a point that's equidistant from the endpoint, there is a perpendicular bisector that would go through that point. So those are the two directions at looking at those theorems. So let's do an example here. BD is a perpendicular bisector of AC. So when they say that, there's a bunch of stuff that gives us. They won't necessarily label all that stuff, but they're telling us that, so it's true. So that AB is equal to BC, that distance is equal. There's a 90-degree angle here. They don't say that, but that's true because they say perpendicular bisector. Also, any point on this line is equidistant from the endpoints. Therefore, CD is going to be equal to AD, or however I rate it, DA or AD. Have AD is equal to CD by the perpendicular bisector theorem that I mentioned. That means that 5x is going to be equal to 3x plus 14. I assume you can see where we're heading here. These are equal. We can solve for x. Once we solve for x, make sure you answer the question. They want us to find AD. Subtract 3 from both sides. We get 2x equals 14. So x is going to be equal to 7. But we have to answer the question. AD is equal to 35. Take the x that you found, plug it back in for what AD's equation is to find 35. The distance from A to D is 35. Okay. Example 2, in the diagram below, WX is a perpendicular bisector of YZ. Again, they're not going to label everything, but by saying the word perpendicular bisector, we know that like YX is equal to ZX and a bunch of other stuff. Maybe some of that stuff doesn't come into play, but you got to realize, just be aware that that is true. What segment lengths, so the question goes on, what segment lengths, I spelled lengths wrong. Yeah, there we go. What segment lengths in the diagram are equal is V on W, the line WX. This line here is V going to be on that. Okay, so just a couple questions that it wants us to answer. What line segments are equal? Well, so I kind of got into that a little bit earlier. So XY is equal to XZ because WX is a bisector, therefore it has to go through the midpoint, cutting this line exactly in half. Also, WY and WZ will be equal because of the perpendicular bisector theorem, theorem 5.2, right? Let me just double check. Is that what that is? Yep, 5.2. I should have just wrote that out rather than say theorem 5.2. The only other one would be VY and VZ because it's given. They both say 25, so those would be equal. Now, the other question is V on WX, this line. If this line extended, would V be on it? The answer is, if this WX is a perpendicular bisector, which it is, V would have to be on by the converse of the perpendicular bisector theorem. Because if any point is equal distance from the endpoints, then it is on the perpendicular bisector. Whether that perpendicular bisector extends that far, is drawn there, or not. That's what that second theorem was saying. So V would be, yeah, the answer to that is V would be on WX. Okay. One more definition here, and then we're done with this chapter. Concurrency. Concurrency is when three or more lines, rays, or segment intersect at the same point. They're all called concurrent lines, whatever it is, lines, rays, or segments. So if three lines intersect at one point, they're concurrent lines. If three rays happen to intersect at one point, we would call those concurrent rays, but often with many of these things, we're dealing mainly with lines. Sometimes with segments, very rarely with rays, but everything applies to rays. And then that point where they all intersect, you can see something here, but that point where they all intersect would be considered the point of concurrency. Concurrency of perpendicular bisectors theorem. Concurrency of perpendicular bisectors of a triangle theorem. The perpendicular bisectors of a triangle intersect at a point that is equal distance from the vertices of the triangle. So what that is saying here, so there's a couple things going on here. Perpendicular bisectors of each side are the blue lines. So what's happening here is the midpoint and then going 90 degrees from that. Okay, those lines, which they're only showing part of it, it would extend both ways, but we're only looking at this part. All three of those segments will be concurrent. So if you take each side's perpendicular bisector, midpoint, and then 90 degrees, and you extend that, these blue lines all meet at one point in the center of the triangle. Well, sorry, it doesn't have to be in the middle of the triangle necessarily, but in this example, it's in the triangle. That point of concurrency is going to be equal distance from all the vertices. So this point that this cursor hand is hovering over right here, is going to be the same distance from A as B as C. This happens for every triangle. Pretty cool stuff. So what I have for you is some bookwork that I'll post and a work packet to work on. Thank you and good day.